Very high. The room. 74.5. All right. So today we have a very brief presentation. We're going to discuss a little bit about uninformative priors, and I think I already threw some concepts here and there, and with some common sense you understand what non-informative prior means. You know, this is slide 46. The previous slides are basically information, we already have seen it, but I put it together so that if you want to look for priors, it's on one source. Okay, but I'm not going to cover them. And I think I may have changed the notation a little bit here and there. You know, I give you a whole table of the exponential family distributions. Things basically that don't add anything new, but you can review them briefly to see what's out there. Okay, so basically when do we use non-informative priors? When really we don't have any knowledge to go one way or another. Okay, and that's most of the problems, you know, if you use non-informative priors. Sometimes you actually use non-informative priors because you rely on the data to make a decision on inference. And using non-informative priors maybe make the calculations easy. Okay, so literally it's a subject you need to know because in the literature you think, oh, there's no prior, I don't see any prior, and actually the prior is there, it may be constant, and you don't, people don't even say anything about it. Okay? Now, usually the way non-informative priors are computed is through the satisfaction of some invariance relations under reparameterization, where you change parameters, so we will talk a little bit about that. So, think that you have a distribution, and your parameter is lambda, and you want to put a prior on lambda, and let's say lambda is a discrete variable, okay? Now, if the variable has k states, you make it a uniform random variable, and you say, okay, I'm going to take as a prior 1 over k. So that's a non-informative prior, but immediately you see the problem that we have with these non-informative priors. What happens if k goes to infinity? You cannot normalize the distribution, okay? So many of the non-informative priors are not proper distributions. That's the message, okay? Which means you will need a minimum number of data to be sure that the posterior is actually normalizable. And we will see, for example, if, let's say lambda is the mean of the distribution, you only need one data point to fix the mean, okay? If lambda is a variance, you will need 2 points. A minimum of 2 data points basically for the posterior to be proper. All right, so let's give one trivial example of a non-informative prior. So let's say we have the coin example. This is the Bernoulli distribution. So you throw a coin and theta is the probability of heads. Theta is from 0 to 1. And we already have seen, right, the conjugate to the Bernoulli distribution is the beta distribution. So the prior for theta will be a beta distribution. And what I'm doing here, let me actually click, okay, good. So for the beta distribution, the mean value is alpha over alpha plus beta, so that as a reminder. So if you have data and you have n1 heads and n0 tails, effectively, when you use a beta distribution as a prior, 1, 1, your posterior will be a beta distribution with parameters n1 plus 1 and n1 and n0 plus 1. Okay? Basically, the counts of heads are you add 1 and the tails you add 1 from the prior. Okay? So this is uninformative because if you put alpha and beta equal to 1, this is uniform. You really get a uniform distribution for alpha and beta equal to 1. So somebody will be very happy, but I want you to look at this posterior and make some, immediately you can see that because you use a beta 1, 1, effectively in the number of counts you added 1 here and 2 there. So someone will say, wait a second, this is not an informative. You will completely change the predictions. Because if you have, imagine that you do an experiment 3 times and you have n1 equal to 1. You add 1 plus 1, that's a lot. So how is this really an informative, non-informative prior? So you can argue on that, so that even the uniform distribution can throw you out, because at the end of the day, what actually even an informative prior does is, it regularizes the solution. So if it happens that you do an experiment and you get no heads at all, and you try to estimate the posterior of theta, somehow here you're not going to get 0, you're going to get 1. Okay? So you may ask, is this really the right the uniform distribution to use? Some people say no. The actual distribution to use is a beta distribution with parameters 0 and 0, which actually corresponds to 2 point masses at 0 and 1, and it's not normalizable. But actually, we will see when we discuss about the Jeffries non-informative priors, the correct actually an informative prior to use is not beta 1, 1, but beta 1 half, 1 half, which is non-uniform, okay? And I will derive it for you, okay? So beta 1 half, 1 half. I mean, nobody's going to tell you anything if actually you use beta 1, 1. As a matter of fact, if you read a machine learning book like Murphy's book, when he gives you map estimate, he throws these extra counts 1 and 2 in many calculations without actually even telling you from where it comes. It comes from using a prior that looks like that. And it's called add 1 sort of regularization. You add 1 count, and that corresponds to this prior. But I will show you that this may be a better prior to use. Okay, so something you need to be careful, right? So imagine that you have a parameter, let's call it lambda, and you're going to put a prior, and you say, I want to make lambda to be uniform. You understand that distributions transform as distributions, not as functions. So if, for example, you change the parameterization, you go from lambda to eta, you know the distribution P of eta is not constant anymore. Should you worry about that? So when you do the analysis, be sure you don't start changing variables thinking, oh, that this is non-informative, is uniform, because if you change variables, you go from something that is uniform to something that is not. Okay? So now, if in the context of the likelihood, this is not an issue, because the likelihood, I remind you, is a function of lambda, it's not a distribution. So really, you can change this as a function, so this doesn't come to play at all. But in the context of priors and distributions, you have to worry about the parameterization. So let me introduce this concept of, I'm going to put all of these things up. Come on. So we're going to discuss this translation invariant prior, okay? And you know the answer, okay? So I'm going to ask you after this slide to tell me what the answer is going to look like. So first, let me take a distribution, and I'm going to define this to be translation invariant when P of x given mu is f of x minus mu. And you can think, actually, if you want to use your intuition, think mu to be the mean of the distribution. So effectively, what it says is, this is a function of x minus the mean, okay? And you can easily show that if you actually slide the mean by a value c and x by a value c, the form of the distribution doesn't change and actually remains the same. This is what we call translation invariant. So I mean, think of a Gaussian, right? You take the mean value, you move it, nothing changes. Okay? So that's why you affiliate this with usually the mean of the distribution. So here is the concept of what we mean a translation invariant prior. It's a distribution that assigns equal probability to an interval from A to B as to the interval A minus C to B minus C for any C. So if I move it by C, right, and I look at the total probability mass that I have, doesn't change. It's translation invariant. So actually what I'm doing is, And I am not going to bombard you on a Friday with integrals, okay? If you start with a probability mass from A to B, and you change some variables, you can write this as this integral from A to B again, okay, just change of variables, and you can see that for these two probability masses, this and this to be the same, P of mu has to be equal to P of mu minus C for every value of C, and the only way for this to happen is for the probability P to be constant. Okay? And that's where the uniform distribution comes, that when you say, what should I use for the mean, and you say, I'm going to use a uniform distribution, that's from where it comes. Okay? It's a translation invariant prior, and P of mu is constant. And obviously, if it's constant, means it's not normalizable. I mean, if I try to integrate this from minus infinity to infinity, I'm going to get infinity. So obviously, this distribution is not normalizable. But if you have one data point only, then the posterior is normalizable. And at the end of the day, that's what you care, right? You don't care about the prior. Is the posterior a proper distribution? If it is, then you're in business. Now, I mentioned, so this constant distribution being this translation invariant. In practice, if you play with Gaussian likelihood, lots of people will use a Gaussian distribution to implement this, where they take the variance to go to infinity. Okay? So basically, if you want to do algebraic calculations that involve a lot of Gaussians, right, you can throw this because you can manipulate this together with a likelihood that is Gaussian by taking sigma 0 going to infinity. The only thing I'm going to say that a lot of these distributions, where to make them uninformative, you push the variance to infinity, they have some pathologies. And there are examples in the literature where you get completely wrong answers. So if you take a regular course in statistics, you will see that. I don't want to discuss those now because they're not going to be relevant to our course. For example, if any of you is going to calculate Bayes factors to compare different models, let's say, there is examples you can show when you use this type of calculations. If you don't do it right, you will get the wrong answers. All right, but at least the constant distribution, we will use it as a translation invariant prior, mainly for the mean of distributions. So let's see the concept of scale invariant. So if a distribution has this form, we call it a scale invariant. The scale basically here is sigma. The idea here is, if you measure x in meters, in kilometers, in centimeters, whatever, it should not matter, right? You should get the same distribution. And you can actually show, if you change the scale from sigma to sigma bar with any constant there c, the form of the distribution remains the same. Okay? So this is what we call scale invariant. And the variable I want you to have in mind, thinking of a Gaussian, is basically the standard deviation, because you remember we have x minus mu divided by sigma squared. So the x minus mu is the translation invariant for the mu, and the sigma is for the length scale. So, and if you want to derive the distribution, basically what you need to say is, look, I want the probability mass from A to B to be the same as the probability mass from A divided by C to B divided by C for any C. So basically it's like saying the probability mass from 10 to 100 should be the same as from 100 to 1000, from 1000 to 10,000, etc. So if you play with the integrals, a little change of transformation there in the integration, it comes out that the distribution has to satisfy this. And you can show the only distribution that does this is the distribution 1 over sigma. Okay? And so this is an improper distribution, because if you try to integrate it, you have the singularity at sigma equals 0, so it will blow up, basically. Okay? So I'm using, when you use this, think of the standard deviation, right? But often you're going to be putting a prior on the precision or the variance, not on sigma. Okay? So I'm going to come back to this shortly. If you want to do, so if you use P of sigma to be 1 over sigma, it's the same as saying the probability of the log of sigma to be constant. And again, you can show this by taking transformation of probabilities, not of functions. Okay? So P of sigma equal 1 over sigma, it's the scale invariant prior. And a way to implement this in practice, because we use the gamma distribution, is to take the gamma distribution with parameters 0 and 0. Okay? And as I mentioned, this is improper, but if you use 2 data points, right? If you have a minimum of 2 data points, the posterior will be proper, so you can normalize it. So this is the example again for this. You can see that the scale invariance with sigma, translation invariance with mu. So P of sigma is 1 over sigma, and actually I want you to remember that if you use transformation of variables, the corresponding distribution for the precision is 1 over lambda. Okay? It doesn't look to you obvious, because from 1 over sigma you go to 1 over lambda. You remember lambda is 1 over sigma squared. Okay? But there is a change of variables, because lambda is 1 over sigma squared, so if you differentiate, you get minus 2 to 1 over sigma cubed. And that will give you, so you need, these are little things that we should not take them light as, they come from transformation of variables. So P of sigma, 1 over sigma, and P of lambda, 1 over lambda. Okay, these are these non-informative scale invariant priors. All right, so now I'm gonna give you a more formal another category of priors that go under the name of Jeffries non-informative priors. Here is Sir Jeffries. Okay, so the concept of Jeffries non-informative prior really comes from information sciences. Okay, and obviously I don't have time or the luxury to discuss this, so I'm going to go directly to the definition. Let's say we have a likelihood function that has some parameters theta. This can be the mean, the variance, or in a computational model can be 50 different parameters. So we define this Fisher information as the expectation with respect to the distribution of x of, these are equivalent expressions. I'm going to concentrate on this, which is basically the second derivative of the log likelihood. Okay, this is a definition. Okay, you may wonder from where this is coming, and when you dig a little bit and you look at Wikipedia, you will see the origin of this is in what's called Fisher information. So we define this to be this the expectation with respect to x, the probability of x of the second derivatives of the log of the likelihood, and then we define this the non-informative prior to be the square root of that. And if theta is many variables, right? We have many variables together. Effectively, this is a matrix, right? This involves derivatives with respect to all the parameters, so this will come to be a matrix, and pi of theta is proportional to the determinant square. Okay, determinant square. Again, you don't really need to know everything, but you need to know that some of the many priors, non-informative priors that you will see in research, are basically Jeffries non-informative priors. Okay, so you need to at least know from where they come. So let's first let's discuss an issue here. So when you look at this, right? So this is a definition, we accept it, okay? Now if it is a definition, if I change the parameterization from theta I go to phi, this equation, when I apply it for phi, it better give me a distribution pi of phi that obeys the transformation rule for probabilities. If it doesn't, then we have an issue. And you remember the rule for transforming probabilities. If you go from theta to phi, basically it's this. Pi of phi d phi equal pi of theta d theta. You remember the probability mass has to be preserved. Okay? So how do we know that the Fisher information actually satisfies this? Well, when you read it on the slides with simple, basically, change of the differentiation from phi to theta, you actually get this equation for free. Okay? So that's a very nice, basically embedded thing. This parameterization is accounted for inside this Fisher information. Examples. And I think I have several in the notes, so I'm going to do only maybe one or two for the mean and the variance or something. So let's take our likelihood to be a Gaussian, and the only parameter that of interest is the mean. So we take sigma to be given. So we have a number of data sets, okay? And the likelihood basically takes this nice form, okay? We have seen these expressions before in the lectures, right? X bar is the sample mean. Okay, so this is what the likelihood is. So to come up with the prior, you take the log of this, so you have this. Take second order derivatives with a minus sign. There's a minus there, a minus, and another minus sign, you get a minus. So this is the answer. Because then you have to take expectations of this with respect to x, and there's not going to be any x involved at the end of this derivative. So basically what you get is you get a constant. Because n is a constant, sigma squared is a constant, so the Fisher non-informative prior is the uniform distribution. Nice. Basically what we got with this translation invariant thing, now it comes also from the Fisher information, it gives us the same answer. If you try to do now the same problem, but for the variance, so the unknown here is the variance only, so you write down the likelihood, okay? And theta here is sigma squared in this equation. Theta is sigma squared. So you take the logs of this, and then you take two derivatives with respect to theta, just algebra with a minus sign at the end. And then we have to take expectation with respect to the distribution of x. So this is where x is coming. So when you take expectations, what is the expectation of this? You remember this thing, if you multiply by n times the n, you really get the expectation of the sample variance. What is that? We did this in the second lecture when we're discussing about central limit theorem and the likes. When you take the sample variance, what's the expectation of that? So you remember, so we multiply by n, that's one n there, and then we divide by n, so that thing with the division would be the sample variance. We need the expectation. What is that expectation? I mean, you remember somewhere I had when we were discussing biased and unbiased calculations, and we did this, right? So if I take the expectation of all of these things and expand it, okay, what do you get when you take the expectation of this? Huh? So you will get the variance, okay, and there was theta cubed, and theta squared will cancel out. So basically, when you put the two things together, this Fisher information is n over 2 theta squared. Theta again is the variance. And when you take the square root of that, n and 2, the constants you don't care, the Jeffries prior is 1 over theta, and explicitly is 1 over sigma squared. Okay? So this is extremely important to remember that the prior, the non-informative prior for the variance is 1 over sigma squared. 1 over sigma squared. Okay? 1 over sigma squared. And if you change coordinates and you go from theta to log of theta, then the probability of log of theta then becomes the uniform distribution. But this is what I want you to remember. The non-informative prior for the variance is 1 over sigma squared. 1 over sigma squared. So I'm not going to go through this example. This is revisiting, basically, you remember I told you that the proper prior for the binomial distribution is a beta 1/2, 1/2, not the uniform. So actually, if you do the Fisher information and you take the square roots, etc., and you calculate the Jeffries prior for the binomial, it comes out actually what you get is this beta distribution 1/2, 1/2. Okay, so so this is, you know, so if you see it, don't be say what is that from where is it coming? It's basically a Jeffries non-informative prior that is conjugate to this binomial distribution. Actually, where you will see a lot of applications in machine learning for sure, if you try to extend this to the Dirichlet distribution, the uninformative version of the Dirichlet distribution will have parameters. You remember the Dirichlet distribution had k states, each of them with their own probabilities. So the uninformative prior will have parameters 1/2, 1/2, 1/2. And you know what? This is contrary to common sense, where if the distribution has k parameters, you say no, 1/k probability 1/k, right? Like a uniform. No, wrong. It's 1/2, 1/2, 1/2, and it's not even the Dirichlet 1, 1, 1, but it is 1/2, 1/2, 1/2. Okay? Common sense doesn't prevail, basically. There are issues with the Jeffries prior, and so one of those issues, there are many issues. We're using the likelihood to compute the Jeffries prior, okay? So you may ask, does this satisfy the likelihood principle? So if I have two likelihoods that they're proportional to each other, do I get the same prior? The answer is, there's examples where the answer is no. And I have one on the next slide if you want to read it. So basically it does not satisfy the likelihood principle. So you have two identical likelihoods that differ by a constant term, and you calculate the prior, it may be basically not the same. And I give you another example here, where I compute the non-informative Jeffries prior simultaneously for the mean and the standard deviation, okay? Simultaneously for the mean and the standard deviation. And if you treat those two variables independent of each other, okay, it comes out that this prior for theta is basically the prior for mu, which is uniform, and the prior for sigma that we saw before, it was 1/sigma, okay? But if you actually do the calculation for both of them being dependent on each other, it comes out that the prior of theta is 1/sigma squared, not 1/sigma. So it's sort of a pathology. If you treat them as independent, you get this. If you treat them as dependent on each other, the Jeffries prior is 1/sigma squared, okay? You know, that's, you know, sort of something, I don't know if it is to be concerned, but something certainly to be aware of. Okay, I need to switch now to something else. Slide 70. Okay. So this, the topic now is going to be about hierarchical priors, an extremely important topic in a Bayesian setting, and not very complicated, but has a lot of new concepts, okay? So imagine you have a model, and your parameters in the likelihood that you try to estimate, all right, are theta, and you're putting some prior on theta, but you are sort of uncomfortable, because you say, really, will this work? You know, is this you know, the right distribution? So what often you do in a Bayesian setting, if you're not sure about theta, you introduce a prior distribution for theta that depends on some other parameters. And let's call those parameters phi. And then for those parameters phi, you put another prior. And that other prior has its own dependence on other parameters, and you keep going like that. The idea is that the number of these parameters phi is less than the number of the parameters theta, okay, that's one thing. And somehow the dependence on phi is weaker than the dependence on theta. So somehow if you stop and you do some assumptions about phi, that model will actually be way better than making directly assumptions about theta. Makes any sense? So for example, and I will show you basically on a table the summary of these different formulations. If you try to compute, let's say, the posterior of theta given x, you may say, I am going to use a point estimate, which is the map estimate. I'm going to only use one point of theta so I don't have to worry about all the values of theta, okay? Well, it's very possible that value of theta will get you out of, will get you in trouble. But if somehow you do this hierarchical modeling and you use a value of phi, not the whole distribution of phi, that may be okay. Okay, and we will discuss this, how this thing is going today. So, for now, so we're going to introduce, so we have theta, and we're going to introduce another, theta is a function of phi now, all right? So our distribution pi of theta is pi of theta given phi, and then we're going to put some prior pi of phi. So if you look at the posterior of for now the new parameters, the original theta and the new hyperparameters phi, as I call them, so this is the new posterior that involves both set of parameters, is really the likelihood. All right? And you notice, by the way, the likelihood depends only on theta, not on phi, because theta contains all the information. Right? If I give you theta, I don't have to tell you from where it comes from. Okay? So this is the likelihood, and this is the prior on theta and phi, which I write it as the prior of theta given phi times the prior of phi. Okay? So again, we are putting a prior on the parameters of the prior. That's what we're doing. With the hope that, you know, as we keep doing this, the significance of the new hyperparameters will be diminishing. Right? It will be diminishing. Okay, so you can actually do this with many, many parameters. Now, ideally, right, if you do this and then you average and you integrate all these hyperparameters phi, that's the best, but really you don't want to do this because it would be way too complex to do. So let me just give you, for the particular example, all the possibilities you may want to. The difficult thing would be to calculate the whole posterior of all parameters. Very few people do this, okay? The other one would be to calculate, to fix, before I had phi, I call it here theta 1, to fix the hyperparameters and compute the posterior of theta given theta 1, all right? So instead of having the, you know, the prior here, you have the condition of theta given theta 1, and of course the other very good thing, if you can do it, is to integrate theta 1 out. Okay, so I'm going to give you a table at the end that summarizes basically all possibilities that someone can do. And actually, let me give you an example first, why you really care about this problem and how, in practice, it's a wonderful tool to use these hyperparameters. It's just not mathematics, but actually you may have reason based on your data to use this model. So let's do this problem. We have, we measure the people in various cities. So, you know, we have a number of cities, and the people in every city is N1, N2, etc. Okay? And we count the number of people who die, let's say, in a certain year from cancer, and we call this people, the number of these people Xi. Okay? So Ni is the population of city I, Xi is how many people die from cancer, and a normal distribution to assume is a binomial distribution. Okay? So basically, for a given city, you can say that with population Ni and probability to have cancer theta I, Xi follows this binomial distribution. Okay? Now, so let's philosophize, right? So, you know, somebody gives you data that come from different cities. What would be the most obvious way to calculate theta I for a given city? I mean, the most trivial thing to do, if I give you data, how, you know, for all the cities, but if you want to calculate, let's say, in South Bend, theta South Bend, what calculation will you do? What would be the most trivial calculation?
Proportion to the cancer rate.
Exactly, which actually, you know what, is going to come to be exactly the MLE estimate for that binomial distribution, for that city. So with that calculation, you will never be using information for what's going on in Chicago, in Los Angeles, in other places. And why is that troubling? Suppose, you know, that the city of South Bend is very small, and you come up that n is very small, and the number of people that have cancer here is like 5. Will you be able actually to do estimation well, if you don't have enough samples, in a small city? All right? I mean, can you conclude basically something in a city that has a population of 50 people versus a city that has 5 million people? I mean, 5 million people, obviously the MLE estimate would be very good, but would it be good in a small city? So the idea here is, how about if we do the estimation of this cancer rate in all the cities all together by linking these theta i's together through some hyperparameters that are computed simultaneously, accounting for all the data in all the cities. And here's how the calculation goes. I am going to assume that I'm going to put a prior on the parameters theta, right? The way you do with a binomial distribution, and the prior is a beta distribution. But I'm going to make this distribution beta to depend on the parameters alpha and beta. You remember the beta distribution is theta to 1 minus alpha, or alpha minus 1, what is it? 1 minus theta, 1 minus b, all right? So when I write the prior for theta I like this, all parameters theta in all the cities are now linked. How they're linked? Because the hyperparameters are the same for all the cities. Do you see that? So I have multiple cities, right? And I'm interested really to calculate theta 1, theta 2, etc. And I can do it independently. But now what I do is I link all of them together because the prior on each theta has these hyperparameters alpha and beta, and those hyperparameters are the same for all cities. So if you go and compute those hyperparameters using your data somehow, and you fix them to some value, then the thetas are already connected because they are linked through A and B, that accounted for the fact that Los Angeles has a few million people population and South Bend has 200,000 population. Okay, all the data come together. So if you write basically, this is literally the unnormalized posterior is the likelihoods, okay, times the priors on theta given eta times the prior on eta, okay? All right, so I am going to show you what the results are, okay? And I'm going to discuss a little bit afterwards on how we compute alpha and beta. So this is 20 cities, okay? So this is the rates of the people who have had died from cancer on different cities. You notice in some places there's 0. I mean, this is on some scale, I suppose, okay? So in some places the number is 0. And this is the population. You see some cities have very high population. And this is the MLE. So the MLE basically, which is the empirical average of the people who have cancer calculated separately for each city, it basically looks like this, okay? So you can see you get 0 there, 0, obviously makes sense, okay? Now, what you see on the plot on the bottom is the posterior mean for each parameter theta, where somehow I have calculated in some intelligent way and I fix those parameters A and B, these hyperparameters A and B, okay? So what you see here is the posterior mean of each parameter, right? This is the posterior mean. And notice the cities that even had 0 MLE estimate, now the MLE estimate is actually rising up. And rising up to this red line, which is actually what I call the pooled MLE, where I do MLE for using all the data all together to calculate one theta. So effectively, for the cities where I had, huge estimates of MLE with very high confidence, you notice these huge bars have dropped towards the average, okay? The same thing there, and the ones that they were 0, they went up. So effectively, what we are doing here is we are sharing information across, the cities to do the estimation of these parameters for every city, okay? This is what's called, it's a Bayesian way to do pooling, right? To use your resources from everywhere to do estimations that otherwise look local. So I'm going to describe on how these parameters alpha and beta are computed. And in this particular case, actually, it is it's not very complicated. Remind me in your homework, did you have to do, there was an iterative MLE problem. What was the distribution in that problem? You remember the last homework problem? There was, it was a gamma. Okay, so a beta here, actually there is a similar calculation. You're going to have to do some optimization in an iterative fashion to do that. Okay, I'm going to describe to you, and actually the same reference that we use for the gamma is the guy who has actually done the calculation for the beta, and I'm going to show you why this is an important calculation, because it comes on this thing. So everybody understands this? All right. So if actually you use the posterior credible intervals, this 95% on the posteriors of the parameters theta, notice, let's look at certain places, right? So if I look at city 15, you notice on city 15, the uncertainty is very small. Let's see what's going on city 15. There is huge number of population. Xi is very big. You know, the MLE is very confident, etc. Okay, so you notice there is very little uncertainty. Okay, let's look at 19, for example. What is 19? Okay, so 19 is here. Okay, so in this case, the MLE estimate looks very big, the same thing as 10. Okay, and now the MLE estimate, basically when you go to the posterior mean, has dropped significantly, okay, because you are sharing now information from the other cities, and you notice on, where is it, the uncertainties on 19 and 10th is significantly higher, okay? And the idea here is, right, that, you know, if you look, let's say, on the city 19, okay, the estimates that you get with MLE are way off from the estimates that you get from the prior. So how is this represented basically in the final results? Is represented basically by saying don't have very high confidence on those estimates, and this is why the error bars are very big. So this is an extremely important thing, you know, when you do experiments, right, and you collect data from different regions of the country, and you try to estimate a disease or something like that, effectively you have to share the resources, and doing hierarchical Bayesian is the way to go. So in the previous problem, the job was, okay, you told us that we fixed this parameter theta, but you didn't tell us to what values. So here's the answer. We're going to calculate, we're going to fix theta to a value eta bar, right? That's why now the posterior of theta becomes a delta function. And how do we define this theta bar? We defined as the maximum of this integral, the value of theta that maximizes this integral. And this integral is actually what is called integrated likelihood or model evidence. So I want you to look carefully on this integral, and do you appreciate that it is like a marginal likelihood, right? What you have on the Bayes, on the denominator of the Bayes rule. This is the likelihood times the prior, integrated all the parameters theta out, but you notice you leave eta as a parameter in the integral. Okay, so you are selecting, you are fixing eta to the value that maximizes this likelihood where theta has been integrated out. There is absolutely no way you will ever do any Bayesian work unless actually you do this type of calculation, because it's very common. Okay, and it has a little bit of a pathology that maybe you have not noticed it to start with. And here's the pathology. So eta, you remember, is part of the prior model, but you notice now that actually you use the likelihood to calculate the prior. What is that? Prior doesn't mean is the distribution before you see any data. Now we see data and we select a prior based on that data. Yes, we do. And that's why this thing is called empirical bias. Okay. So if you search, on Wikipedia, you will come up that this is the way to do. And a lot of times, even if we don't have it, I call this model evidence. But really, the concept of evidence comes in this context of hyperparameters. So it's really the marginal likelihood as a function of the hyperparameter theta. So what you do is you maximize this, and the value, you fix it, and you do your calculations so that fixed set of eta. Okay? And you may say, well, on this problem with the diseases and everything, with the cancer rates, can I actually calculate this eta sort of exactly? And the answer is yes. And here is how this marginal likelihood looks like. Okay? Somewhere, you remember, in passing, I showed you how you calculate the normalizing factors and posteriors. I know it was complicated formulas here and there, but somewhere I discussed how you calculate normalizing factors. So if you try to integrate the parameters theta out, okay, this was the anormalized posterior, so if you try to integrate things out, what you get is, from the binomial, you get this factorial term there. And then, what you will get is, you will get the normalizing factor from this distribution, which is that, and then you will get a normalizing factor from the posterior from the product of the two. You have to trust me, basically, okay? If anybody has questions from where this is coming, you can actually explicitly put the, what this binomial is, right? Put this beta distribution explicitly, and then you will see that what you get is, you get basically this model evidence to be this ratio of these products of the beta function, okay? And I think this is similar to what you did in your homework with this iterative MLE, right? So here, Minka, in the same paper, he gives you a way to calculate the gradients of this with respect to A and B and find these point estimates to maximize this model evidence. In most occasions, you are going to have to use an optimization software to do this. You won't be able to do it analytically, but one way or another, you will have to calculate quantities like this. Okay? All right. So what I want to do is, because there is another example that is very nice, maybe I will do it on Tuesday, I wanted to summarize for you all possibilities that exist in this hierarchical Bayesian analysis. The most trivial one is maximum likelihood. Look at this again. You only have theta parameters, and what you do is you maximize the likelihood, you fix it, no posterior, no nothing, no prior, nothing. Line 1, we agree? MLE. Look now, the second line, you calculate the posterior, forget eta. You can take, there's no eta here. You maximize basically the posterior, and you set the parameters theta to this theta hat. That's your map estimate. Okay? Now, this is what we did today. You are going to calculate this hyperparameter eta, and that you will fix them, and you calculate them by maximizing the evidence. And the evidence is basically the integrated, is the normalizing factor likelihood times the prior for a fixed theta. Okay? This is the model evidence. This is empirical Bayes. Okay? So this is basically the standard way for most of the people who try to deal with these hyperparameters. A more advanced way, instead of actually having here the prior of theta given eta, you're actually going to throw in the prior on eta as well. So in principle, when you write this, it's like saying the prior on eta is uniform, okay? But here you're throwing the prior eta as well, which means effectively this becomes this marginal likelihood given eta times the prior of eta. Okay? So you maximize this with respect to eta, and this is map 2 estimate. Okay? And if you really want to do everything perfectly, you calculate the posterior of both theta and eta. So you basically take the likelihood times the prior of theta and eta, and hopefully you can find the means to explore this posterior. So this is not Bayesian, the first one. The second one looks like Bayesian, but a point estimate is not really Bayesian. When you do this, all the three analyses, even though you use point estimates for eta, they're really Bayesian formulations. You use point estimates for eta, but you compute the posterior basically of the parameters theta for a fixed theta. Okay? So there is another example that I have in the notes. You can maybe read it. So we can do it fast on Tuesday. It basically tries to calculate the average grades in a statistical class, averaged over schools, and they say Notre Dame is an outlier. Okay, so you have to do pooling to account for good grades in other classes at Notre Dame to basically balance things, and that's what this example is. Okay, it's very similar actually to what we did with the counter rates, but the distributions are continuous, so you get some nice results. Okay, so we will come back actually to this example, and then we will take baby steps to start reviewing Bayesian regression sometime next week.